Good morning, grade 11. So, the next part of our geometric optics work that we want to take a look at then is we want to start talking about different properties of light, not just reflection and refraction. So, the next one we want to take a look at then is absorption. Now, absorption is an incredibly important part of the work because it's the reason you perceive things to have different colors. Now, visible light covers a very wide range of wavelengths in the electromagnetic spectrum. And what you need to remember about actual light is that when we talk about something called white light, then we're actually just talking about all the different wavelengths of light. Your reds, greens, violets, blues, yellows, orange, everything together that is traveling in the same direction and being reflected off of objects and so on, and therefore we perceive it to be white light. Okay. The other one then is black light. Okay, and I'm not talking about the one you guys freak out when you go and you're in a club somewhere where you're not supposed to be. I'm talking about the absence of light. Now, black light does not exist. There is no such thing as black light. You can't go buy a torch and it shines black light. Okay? We refer to the color black or black light as a phenomenon where there is no light being reflected. Okay, that means that when we're dealing with white light, the object that the light is hitting, if it's, let's say, a white car, then all the light is being reflected off of that object. Where if it was a black car, then we would say that it's black because none of the light is being reflected, so all of the light is being absorbed. Now, what's very important, and I see there's a little mistake here in the slideshow. So it says white reflects all light and absorbs none. Black reflects no light and absorbs none. It should actually be that black reflects no light and absorbs all light. So I'll just fix that there for you. There we go. That's better. Okay. Now, if we take a look at the two examples on the right-hand side of the screen, we've got a little red ladybug there. Now, what happens is that white light hits this little red ladybug. The actual molecular structure of the molecules that makes up that ladybug's shell, every single molecule has a different frequency of light that it can absorb. And in the case of the ladybug, the molecules that make up its shell absorbs all the incoming wavelengths or frequencies except for red. And red is therefore reflected away from the object, and we perceive the ladybug to be red. The same thing that happens when we take a look at a green leaf. So with the green leaf, and what you'll remember from life science and so on, and your natural science and so, is where you learned about your chlorophyll. Now, the molecular structure of that actual molecule absorbs every single frequency of light. So it absorbs all the incoming light except for green light. The green light is reflected, and it's due to this green light being reflected that we perceive leaves to be green. The next one that we want to take a look at then is transmission of light. Now, what is transmission of light? Transmission of light is it happens when light passes through an object. Now, it's very easy for light to pass through certain objects, but more difficult for light to pass through other objects. So if we take a look at the little window that we have here on the bottom right corner, where we're going to deal with the three different types of transmission. So the first very easy one, transparent, like an open window or even just looking through the glass. It's transparent, most of the light passes through it and we can clearly see the object on the other side. Then we have translucent. Now, if you've ever gone to visit your grandmother, or even maybe your mother has got a thin material that you can see through behind the curtains to protect protect it from damage from the sunlight. And this is what we refer to as a translucent material. Light passes through the material, but some of the light is absorbed by the material, so we can still clearly see the object on the other side, even though not all the light is passing through. And then we get to our obscure materials. Now, obscure materials is like thick curtains that you have in your bedroom that keeps out all the light. It's the reason you can sleep till 2 o'clock in the afternoon and you still think it's dark outside. Now, if we take a look at our object here at the top, our little red ruby that we have there, another very important thing to understand about transmission is that transmission and absorption goes hand in hand. Now, a ruby is red because of its actual structure, because of its chemical structure, its molecular structure, because of the molecules that makes it up. So when white light enters the ruby or hits the ruby, everything is absorbed except for the red light, which is transmitted, and we then perceive the ruby to be red. Now, it's very, very, very important to understand is that when we are dealing with transmission and absorption, and if we take a look at the bottom left-hand side there, we can see that when we have an incident ray, let's say hitting something like a glass window, some of the light is reflected. Some of the light is absorbed, because if you put your hand to a window that's been in the sun the whole day, you can feel it's warm. And some of the light is actually transmitted through that window, which it has to be, otherwise we wouldn't be able to see what's on the other side. The next thing I want us to take a look at then is the speed of light. Okay? Now, speed of light is a universal constant, and we can define it as saying the speed of light with the symbol lowercase c is a constant and is in a given medium and has a maximum speed in a vacuum of 3 times 10 to the power of 8 meters per second. Now, that's a universal constant, and somewhere you would have heard the things before of nothing travels faster than the speed of light, which is the truth. Okay? Now, if we compare sound at sea level, in other words, your mom calling you from the kitchen, how fast that sound gets to your ears, and the speed of light, we can see that the speed of sound at sea level is 340 meters per second, whereas the speed of light is 299,792,458 meters per second. That's a very, very large number, and light travels incredibly fast. And we can see that as we convert it to kilometers per hour, it just gets bigger. As we convert it to feet per second or miles per hour, which we won't do because we do not use the irritating American system. But you can see the value just gets bigger and bigger and bigger. Now, this creates a problem for us because, like we've learned in science, we try to work as easily as possible, and if something is too complicated, we try to make it less complicated. Now, the way that we do this is by we start talking about something called light seconds, light minutes, light years, and that's just a way for us to describe distance between stellar objects like the Earth and the Moon, the Earth and the Sun, the Earth and Mars, and so on and so on and so on. So when we're dealing with this, we're working with the speed of light as 299,792 kilometers per hour. That would mean that the distance between the Earth and the Moon is 1.3 light seconds. It means that light takes 1.3 seconds to travel from the Earth to the Moon. Okay? Now we can of course go and we can multiply that by the actual velocity of we can actually go and multiply that by the velocity of light to calculate the actual distance that it traveled. But it will be a much smaller value just to work with the light seconds. Then we get to the Earth and the Sun. The Earth and the Sun is 8 light minutes apart. So that means the time or the distance that light covers in 8 minutes. Okay? If we take something bigger like Earth to the far side of the Milky Way galaxy. In other words, the furthest side of the galaxy from where we are situated. It's 52,000 light years. So that would mean, to calculate the kilometers, we would take the 299,792 kilometers, and it's per second, so we have to multiply it by 60 for seconds, multiply it by 60 for minutes, multiply it by 24 for hours, and then multiply it by 265 for years. And then we would get our actual distance covered. So it makes it a lot easier for us to actually work with these incredibly large distances. Okay, so I'm going to stop there. The next lesson we will go on then with refraction.